This is the video recording of Lesson 2-6, Day 1, and I want you to grab your yellow learning objectives, because this one is a biggie. You know, if we can get this whole graphing down, then every time we deal with translations and families of functions like this, we're going to be that much better off, and you'll think this is easy. Section 2.6 and 2.7 are lumped together, and it says I can apply translations of functions both graphically and algebraically. So translations of functions. Translations are telling us we're going to do a slide, you know, right, left, up, down. In geometry, it was called a slide, a glide, but translation is the fancy math word for it. So what you'll want to do for this section is have probably at least 3 colors to write your notes in. It is a big help to you when you look back at your notes if you have things color-coded as we talk about families of functions. So maybe pause the video and go grab those. Now, our objective from, again, 2.6 and 2.7 is to analyze transformations of functions. And you'll notice this doesn't say translations, it says transformations, but a big part of that, a chunk of that is the translation piece. So transformations are any changes that we can make to a function by putting new numbers in, putting numbers in lots of different positions. But what we want to learn about is how can we tell what's going to happen just by looking at the equation. And that is going to be the key to us understanding the transformations. So we have families of functions, and that's a set of functions in which each function is just a transformation of a special function called the parent. So lines. Lines are a family of functions. And the most basic one would be the line y equals x. No numbers in there, just y equals x. And if you think about it, you'd say, well, Cedar, there really is a 1 in there. Y equals 1x. So it's the simplest function from the set. So like it says in the example, linear functions are lines, root word. Linear functions form a family of functions with the parent being y equals x. All linear functions are transformations of that parent function. So we have different types of transformations, and those could be vertical translations. Those are moving it up and down. We could have horizontal translations, which would be moving it right and left. We have reflections, which are just what it says, a mirror image of what we had, and it might be a reflection over the x-axis, a reflection over the y-axis, a reflection over the origin. We can reflect over an infinite amount of things. And then we have a vertical stretch or compression. And what I need you to think of when you think vertical stretch or compression is making the function out of a rubber band. And if you hold it at the top and the bottom and you stretch it out, you're doing a vertical stretch. And if you take that rubber band and you squish it down, then you're doing a vertical compression. But what we want to learn is what types of numbers do these things. So first up, translations. That's just going to be the objective that we talked about from this section, which is finding out, you know, slide it, glide it, left, right, up, down, where does it go? So it moves the graph of the parent function vertically, horizontally, or maybe both. And it doesn't change the shape or the orientation of the parent function. So it's not a transformation, it's a translation. So that means the shape is held. And orientation has to do with reflections. You know, how you look in the mirror and you're backwards. That's not going to happen with these. So it's literally just like taking the function and sliding it left, right, up, down. So down here, it says if the parent function equals f of x, so some function, and k and h are positive constants, well then if we have f of x plus k, and notice the k is outside the parentheses, that plus k is going to move the graph up. If outside the parentheses of f of x we have a minus k, well, logic tells us that's going to move it down. So for both of those, notice that k is not in the parentheses. The big deal with that is that means it's not attached to the x. It's separated by those parentheses. Now, x is responsible for those movements right and left. And so what we have to know about that is they're always backwards from what we think they should be. So if we see f of, and inside the parentheses, it's x minus h, so x minus 1, x minus 3, x minus 57, that actually moves the graph to the right. And if it's f of x plus h, we need to think opposites. That's a negative h. That will actually move that graph to the left. So with k, which is the number out in the back, no parentheses, it's logical. Plus is up and minus is down. But because x reacts the opposite of what we think it would react, f of the quantity x minus h actually moves to the right, and f of the quantity x plus h actually moves to the left. So here's what we want to see. It says adding k to the outputs shifts the graph. So here's what I'm looking at first, and here's where I want your three colors. The one in the middle is just f of x. So I'm going to color code that one, the red that they already have here, and I'm going to put arrows on the end because I'm going to assume that that just keeps going. And I notice that with the green one, this says f of x minus k. And I remember, if it's outside the parentheses, it's logical. So minus k should move it down. Logic tells me that. And then, if it's f of x plus k, where k is outside the parentheses, then that should move the red one up. And it did. So now, like I said, with it color-coded, it's going to match, and you'll be able to take a look at those colors. And those black and white packets, that's not going to help you out very much. So now I need to fill in that little blank. Adding k to the outputs shifts the graph up. When we add k, it's logical. Plus is up, minus is down. But with horizontal translations, which is what we have going on right here, I start with f of x, which is red. And now I notice that my shifting is inside the parentheses. So I take a look at the green one, and I say, x is attached to that, and x always behaves the opposite. So that's actually going to move things to the right, and it does. So f of x minus h actually moves it to the right. And then the blue one moved it to the left. Well, again, to the left we'd normally think negative, but it's inside with the x. So it has to be the opposite. That's going to be f of x plus h. Now, this is the biggest concept that everybody has to get in their noggin as we talk about families of functions. Because up and down is normal. Up is positive, down is negative. But if it's attached to x, it behaves the opposite of what we see. So subtracting h from the inputs actually shifts the graph to the right. So that f of x minus h is a shift to the right that we see in the green there. So again, that's the key, remembering that anything attached to x is the opposite of what we have. So problem 1 says, how are the functions y equals x and y equals x minus 2 related? Make a table of values, and how do the y values compare? So first off, y equals x is exactly that. Whatever x is, y is exactly the same thing. So we can just copy down those values. But now the next one says, well, we want you to take the y equals x, but then we want you to subtract 2. So I'm going to take what I have in the middle column and subtract 2. And it says, how would these two be related to each other? Well, it has a minus 2 in the back, and it's not in parentheses with the x. So that should be logical. This should shift the graph. Y equals x shifted 2 units down. Now, as we get further along, we don't want to use the word shifted. We want to use the fancy language, translated 2 units down. That looks like an M. Spelling issues. There we go. Hand and brain working together. That's how it should be. So translated 2 units down. Now, how are those graphs related? Well, we already know. So what we have to do is graph what was in the black, which was our 1, 1, 2, 2, 3, 3, 4, 4, etc., 0, 0. This is the line y equals x. Really important line, so don't forget that the line y equals x is the perfect diagonal through first and third quadrants. Now we go back and we check the table and say, well, here's my x and here's my y. So I have to have this graph at -2, -4. And I realize, well, because I know it's going to move 2 units down, all I have to do is take all those dots I had on there before and move each one of them 2 units down. So this is where it becomes a huge time saver to know what the numbers are doing, and that if they are not in the parentheses, that they are logical. Plus is up, minus is down. All right. So when we talk about that shifting, we want to use that fancy language of 2 units down. Now when it asks us how in those table of values do they compare, well, what we'd want to say is we subtracted 2 from each of these. So what happened was each y value had 2 subtracted from it. But again, what we use that for is to say, well, it wasn't attached to the x, so that means it was moving this 2 units down. And so this is really the answer to how the graphs are related. Now in the future, we're not going to stop and explain that, hey, we subtracted 2 from each of the y values that we had up there. What we want to do is constantly compare these to the parent function. So when I do a graph, I want to label, hey, this one is y equals x, and notice how I changed colors here. This one is y equals x minus 2, so that somebody that's looking at it can see, oh, look at that, it was just 2 units down from where it was before. Now, we come to C. And it says, what's the graph of y equals x squared minus 1? And we want to put that up 5 units. So I start thinking, okay, if I'm going to put it up 5 units, then I'd have to tack a plus 5 back here. But wait, -1 plus 5, that's going to be y equals x squared plus 4. Because those are like terms, they're both constants, and we can put them together. So here's what we do. We say, I'm going to graph the parent function for this graph, which is just y equals x squared. Remember, no numbers or anything in it. It's as basic as it can come for x squareds. And I'll do -2, -1, 0, 1, and 2, and I'll square those numbers. And -2 times -2 is -2 squared, so that's 4. -1 times -1 is 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. And yeah, you can think -3, 9. That's also going to be on there. And you can get those points graphed. But this time, don't connect them up. Don't get ahead of me here. Don't connect those. That is the parent function. Now, we want to put some dashed lines in here to remind us this was the parent. This is not my final answer. Anything in math that is a helper graph, which is what this is right now, helpers are dashed. Your final answer is solid. So now I want you to change colors. I'm going to make mine match the red here. And when I added 5 to that, it became y equals x squared plus 4. So that means I have to take my green graph, and I just have to count. Each one of those points I put on there needs to move 4 units up. So I'm going to start at the vertex, 1, 2, 3, 4. And then I'll go to -1, 1, 1, 2, 3, 4, 1, 1. and my 2, 4, and negative 2, 4. And now that is a solid graph. And I label that one y equals x squared plus 4, because that's my final answer. So they wanted to know, what is the graph translated up 5 units? Well, there it is. And I also know that this is the equation for it, because when you have up and down movements, up and down translations, that doesn't change your x value. It's not included with it, or there would be parentheses. The got it says, how are the functions y equals 2x and y equals 2x minus 3 related? So here's what they're doing. They're asking us for similarities and differences. And I look and I see, oh, there's the similarity. They both have the y equals 2x. So basically, they both have a slope of 2, which is great. But the second graph has a minus 3 in the back. So here's what I'm looking for. Does it have parentheses? Because if it has parentheses, then it's with the x, and I have to think opposites. If it doesn't have parentheses, then it's normal. Plus is up, minus is down. Oh, there's no parentheses. It's going to go down 3 units. Translated, it's y equals 2x, translated 3 units down. That's what it is. So, how are the graphs related? Well, that's exactly what we just did. Y equals 2x will translate 3 units down. So in A, when it says how are those functions related to each other, you could say, if I made a table, all the y's would be 3 less than they were before, so we can put that on there. If I made a table, all the y values would be 3 less. But really, we kind of skip that step because we don't want to use tables. What we want to do is get a parent function that we recognize and know what it looks like, and then we just want to move it. We want to translate it. So instead of stopping to say, hey, if I made a table, I'd subtract 3, we should really go immediately to, I'm going to translate this 3 units down, and that will tell us what we need to do. So in C, it says, what is the graph of 3x translated up 2 units? So I think, all right, in my first color, I just have to graph y equals 3x. But this is my helper graph, so this is going to be dashed. All right, y equals 3x. Y equals mx plus b. If there's no number in the back, what number was really there? They added nothing. Oh, that's 0. So I'm going to start at 0, and then I'll use 3 as my slope. So I'll go up 3 and to the right 1. And since I'm really bad at drawing straight lines, I am going to do that several times so that I have something to aim at. There are so many shadows on the smartboard. Oh, and then I started doing it solid. This one has to be dashed. Getting ahead of myself. There we go. All right, now I'm going to change colors, and I want to translate this up 2 units. So I start thinking, okay, up and down are normal. So that should be y equals 3x plus 2. But hey, if I'm supposed to translate it up 2 units, I'm not even really going to worry about what the new equation would be. I'm just going to count. So I'm coming over here to all those lovely little points that I had, and I'm going to move them up 2 units. And when we get done, we draw this solid line and label it y equals 3x plus 2. Now it should be parallel to the line that we had up there because it has the same slope, but it's just been moved up 2 units, and there it is. So again, by learning the positions of the numbers and what they do, we can go ahead and get these graphed really quickly without having to make a lot of tables. This says the graph shows the projected altitude, which is f of x, of an airplane scheduled to depart an airport at noon. If the plane leaves 2 hours late, what function represents this transformation? So I'm going to look at this graph. And I see in the black they had the original. So there was the plane trip. And I want to think about what that means. People were here at the airport, and then the plane went up high, leveled off for just a little bit. Then it was ascending again, leveled off for a while again, and then they must have gotten closer to the airport because then it went down, it descended, and then boom, really descended to get into the airport. Now, this blue graph over here starts at 2, and it's exactly the same graph, just shifted over 2 units to the right. So I think, okay, this is not the k value. K value was outside the parentheses because this is right and left. It has to be attached to the x because x is responsible for right and left. So it's f of x something. Now what else do I remember about things with x? Oh, they're always the opposite of what I think they should be. So if I go 2 to the right, I would be thinking that's a plus 2, but it's not. It's a minus 2. So there it is. F of x minus 2. Whatever you have with the x, think opposites. Now this says, suppose the flight leaves 30 minutes early. Let me get this so you can still see the graph. Well, first off, the information about this graph says hours after noon, so I can't use 30 minutes. I'm going to have to use a half an hour. And secondly, a half an hour early, well, that's going to move it to the left. So now I think f of, okay, so normally left I would think is negative, so it has to be a plus in the formula because it's attached to the x. The x always responds the opposite way that we think it will. So right appears as x minus and left appears as x plus. Now, the other kinds of transformations that we can have. We can have a reflection. Reflections are an equal but opposite distance on the other side of whatever it is you're reflecting over. So it flips the graph of a function across a line, such as the x-axis or the y-axis. And the original points and the reflected points are the same distance from that line of reflection. So all we have to remember is equal but opposite for reflections. Equal but opposite. Now, if we reflect in the y-axis, so write that in one of these fancy colors, and then underline this. If we reflect in the y-axis, the x values change signs. Not the y's stay the same. So f of x becomes f of negative x because the x values change signs. If we reflect in the x-axis, so write that in a different color. If we reflect in the x-axis, the y values change signs, so underline that. And f of x is y, so f of x will become negative f of x. So here's what you have to remember about reflections. You have to think about the opposite. If they say reflect over the y-axis, make the x's the opposite of what they are. And if they say reflect over the x-axis, make the y's the opposite of whatever they are. So reflecting in the x and the y-axis are not that big a deal. So down here, I want to find where the original was, and the original was in the black. And I see the one in the green, and I'm thinking, well, they must have reflected that over the y-axis, because it looks like it's equal but opposite over here. They did. So if they reflect in the y-axis, all the x's should change signs. 3 became negative 3. 1 became negative 1. 5 became negative 5. And one last point here. Oh, well, the other ones they didn't label. They just wanted to give us enough to take a peek here. So the reflection of f of x, that's the reflection in the y-axis. Each one of these has 5 points that it's made up of. So if we were going to do this reflection by hand, we'd want to know all 5 of those points. Now the next one says, we're in the blue, And I see how that has turned this upside down, so that must have been a reflection over the x-axis. So if you reflect over the x-axis, your y's have to change. Opposites. This was 1, now it's -1. This was 4, now it's -4. This was 1, now it's -1. So the opposite is what we're looking for. Reflect over the x-axis, the y's become negative. Reflect over the y-axis, and the x become negatives. So this is a reflection of f of x in the x-axis. Equal but opposite over the x-axis. So reflections even, that you can see that we're talking about things that are going to have the same size here, but we've changed their orientation when we flip them over a line, when we do that reflection. So problem 3 says, let g of x be the reflection of f of x in the y-axis. I'm going to go ahead and underline that. What is the function rule for g of x? All right, so it started like this. F of x equals 3x plus 3. And if I am supposed to reflect it over the y-axis, that means the x becomes negative. Well, we wouldn't leave it like that. 3 times negative x is negative 3x plus 3. And they said, give it this new name, g of x. So let g of x be the reflection in the y-axis. What is the function rule? Well, there it is. Because if you're going to reflect over the y-axis, you have to make the x negative. And then it says, for a reflection in the y-axis, change the sign of x. Well, they're even giving it away to us. We did that. And evaluate it and simplify. Yeah, we're not going to leave it 3 times negative x. We changed it to negative 3x. And then it says, check by graphing both f of x and g of x. All right? So I'm going to color code. F of x is 3x plus 3. Y equals mx plus b. That means I'm going to start on the y-axis at 3. And this has a slope of 3, so that's 3 over 1. I'm going to go up 3 and to the right 1. And then I'll use the slope backwards because, again, I really like to have a few more points to graph. And that's my original. And they did want us to graph both, but I'm going to go ahead and make this one dashed since this is the one before the transformation. So that makes it my parent. All right, now I have the other one already written in red, so I think I'm going to go ahead and use that. G of x is negative 3x plus 3, so I would still start at 3 up here, but I'm going to have to go down 3 and to the right 1. I'm going to do that a few times, and I'll use the slope backwards, so left 1 and up 3. And this one I will make solid and label that as g of x equals negative 3x plus 3. So now what I want to see is, does it look like it's equal but opposite on the other side of the y-axis? So these distances should be the same, and they are. Those two distances are the same. So even though I manipulated the equation, when I graph it, it makes sense. It's reflected over the y-axis. Now this one says, let's let h of x be a reflection of 3x plus 3 in the x-axis. Well, the first thing I have to do is realize that f of x is y. Remember, that's just fancy function notation that tells us that, hey, this was a function. And now what I have to do, because I want to reflect over the x-axis, is make the y negative. But we look at that and we say, well, that's not right. We want that in slope-intercept form. So we would multiply or divide everything here by -1. And then they wanted us to give it a fancy name. They want it to be called h of x. So it's important that we're following the directions and we're changing that and making the name the new name that they wanted it to be. So again, you reflect over the x-axis, make the y negative. You reflect over the y-axis, make the x negative. And that will take care of those reflections for you. And there's day 2. And we are not done with our objective of talking about all of the translations and transformations, because we haven't seen all the different families of functions that there are, but we're going to learn a lot about them. So with day 2, we'll finish this up for now. This is the assignment for day 1. And yes, there should be some graphing in there. Again, you're not forced to use graph paper if you don't want to. But it is in the black file folders in Schoology if you want to print some of that graph paper off. But there it is, section 2.6, day 1.